Okay, so today we're going to get back to looking at gradients. Gradients are, as we'll see, important for optimization as well as for understanding whether optimization algorithms work. So yesterday we said, or Monday we said that the gradient tells us the direction of maximum increase at a point on the cost function. So if we're sitting here, that means this is the quickest uphill direction. And then it also tells us the slope, how steep things are here. And in particular, when you look at that gradient vector, the norm of the gradient vector tells you the steepness, and the direction of the gradient vector tells you the direction of maximum increase. So this points uphill from where you are. Now, of course, you'll notice that uphill is not usually pointing straight at the maximum. In order to, go to the maximum, you kind of have to take a curved path. So we'll talk about that a little bit later. And we're going to be assuming that we have these differentiable functions where the gradient exists everywhere. So we define the gradient. If we have some parameters we're optimizing, they could be a vector, they could be a matrix, they could be a scalar. The gradient is just basically you could say the matrix of partial derivatives with the same shape as the parameter you're optimizing. And we looked at a couple examples. And so now we're ready to talk about first order approximation. Okay, so for this we have to remember the Taylor series of this function. And we're going to start with scalar input functions. So this is the simple case where we just have one scalar parameter that we are optimizing. So the Taylor series at the point W naught is going to be the function evaluated at W naught plus the derivative of the function with respect to W evaluated at W naught times the deviation from W naught. That's the first order term. And then we have a second order term which contains a second derivative and squared deviation. And we have an infinite series of other terms. And so if we want to write the full Taylor series of a function, this could be quite complicated because we have to do all these terms and there could be an infinite number. So usually we don't really care about the details of those higher order terms. For our purposes in this unit, we will just say that these things are no bigger than quadratic in the deviation. And we express that idea using this big O notation. Big O notation. Okay. So, roughly speaking, when we say something is order epsilon squared or big O epsilon squared, that means that the magnitude is at most a constant times epsilon squared when epsilon is close to 0. There's another version of this that handles when epsilon goes to infinity. But in this case, since we are looking at small deviations around this point, we are interested in when this term is getting small. Okay? So this is sort of the informal understanding. And then the formal mathematical definition is that there exists some positive constants, C and delta, such that you can upper bound the magnitude of this. If some function g is order epsilon squared, it means you can upper bound the magnitude of that function by a quadratic capital C epsilon squared for all epsilon in the open interval, all epsilon in the open interval between minus delta and delta. So that's the full mathematical definition. But you can think of this as basically like this term is no bigger than quadratic for a region where this is small. Okay, so let's take a pause. How many of you guys have seen this big O notation? Okay, great. Any questions on anything regarding big O? Okay, so we'll be using this a bunch. So the other thing I want to emphasize is that this equation is an exact equality. So this function JW is exactly this big complicated thing. But because of the complexity of all these higher order terms, we are often going to approximate the function by the Taylor series approximation. So since we're going to do a first order Taylor approximation, that means we're going to keep only the terms up to the first order and get rid of all these other terms. Okay, so we no longer have an equality, now we have an approximation. And in particular, that approximation is going to be J at omega naught plus the derivative evaluated at omega naught, W naught minus that deviation. Okay. And when we do this approximation, we can immediately see that the error in the approximation is exactly this. This is the part we threw away. So in other words, the error is no bigger than this deviation squared, at least for W, in some open interval around W naught. Okay, so here we have a pictorial example of some function, J of W versus W. And then here we have a reference point, W naught. And this line would be the first order Taylor series approximation. So we can see that when W equals W naught, then this goes to 0, so this goes away, and we have a perfect equality. Right? So the approximation is perfect at that point. And as you go away from the point, the approximation tends to get worse. But it gets worse at this rate, no more than quadratically. Okay, so that's the idea behind the first order Taylor approximation. So we're going to use this for a couple derivations, and we'll see how this is, we'll see how to apply it in a moment. Okay, so these are the main ideas of the Taylor approximation, or the first order Taylor approximation. Any questions on what we have here? Everybody good with this? Okay, so we've done this for scalar input functions. Now we want to repeat this for vector input functions. So this would be if we have a vector of parameters W1 through WD that we are optimizing. So this function is scalar output, but the input is d-dimensional. So now we're going to have a reference point, which is also d-dimensional, still W naught. And now the first order Taylor approximation, it's really in spirit the same idea, except that now we're going to have a sum of these scalar derivatives, but the sum is going to be over each of the scalar variables in this vector. So we're going to have one of these for every one of those variables, and we're going to have one of these for each of those variables. Okay, so the way this ends up looking is we have J evaluated at the reference point plus a sum over our D coordinates, J going from 1 to D, of the partial derivative with respect to Wj evaluated at the vector W naught times the deviation from the reference at the jth entry. And now, rather than writing out all the other terms here, I'm just going to write basically the sum of those guys. Actually, yeah, I'll write it that way. So now we're going to have plus j equals 1 to d of, big O of wj minus w reference j squared. Okay, is that idea making sense? So it's the same, it's just that we have now the sum over the different entries in this vector. Okay, now we can rewrite this in a way that might bring us some intuition. So the first thing we can notice is that this quantity is the jth element of the gradient vector evaluated at vector w naught, right? Jth entry of the gradient vector based on how we define that gradient vector. And this is the jth entry of the deviation vector w minus w naught. And so that means that this term here has this form, which looks like a product of one vector times another with a transpose, right? Okay, so that's how we go to here. And we can look at this. So, so here we have the sum of these big O terms with scalars, but we can actually move the sum through that big O, and then we just have the sum of those elements, which is nothing more than this Euclidean norm. Okay, so this becomes this guy. Everybody with me so far? The very last thing we can do is we can take the approximation, which means we get rid of this big O term, and then we can rewrite this using slightly different notation. This is the inner product notation, the official inner product notation with the angle brackets. Because when we deal with real valued vectors, let's say any real valued vectors A and B, finite dimensional vectors, the inner product between A and B is basically this, A transpose B. And interestingly, we can interpret the inner product as something to do with the angle between those vectors. And the way to realize that is you can always write the inner product this way, where you have the norm of A times the norm of B times the cosine of the angle between those vectors. So it's like you have A and B, and then you have this angle theta. So no matter what space you're in with two vectors, you can talk about the angle between them. Okay, so at the end of the day, we see that J at an arbitrary point W is approximately equal to J at the reference plus the inner product between the gradient and the deviation from the reference. So that's what that means. Then this approximation is good when W is close to the reference. Okay, great. Any questions on this? Okay, so we've done the scalar case, we've done the vector case, we can do the matrix case, but we're going to do one other thing first. Remember that we said at the beginning, way over here, made this claim that the gradient tells us the direction of maximum increase as well as the slope at that point. So maybe we can actually prove this now. So we're going to prove it using this Taylor series expansion. So we're going to look at something called the directional derivative. How many of you guys have seen the directional derivative? Okay. So what you do is, so you're in some space that's larger than one-dimensional, two or more dimensional, and you choose a direction to go in. And you name that direction u. And in particular, u is going to be some vector which has a norm of 1, so it doesn't really have any fancy length, but it does tell you the information about the direction you want to look in. So maybe we are here. This should be like W0, W1, and then this could be J of the W vector would be that surface, and this would be the reference point, W0, the vector. And so now I'm going to look in this direction. That would be like my u. I'm going to look at this direction in this two-dimensional plane. And essentially, I want to know, the directional derivative tells me if I'm traveling on this surface and I'm looking in this direction at that point, what is the slope in that direction at that point? So that's the slope, which is going to be the rise over the run. Right? And so here you can see we have the rise over the run. We're going to move epsilon, some small number, epsilon, in the direction of u. So the total distance we're moving here, the total norm is epsilon. And so this is the difference between where we were and where we're going, divided by epsilon, which is the length we've traveled. Is that directional derivative making sense? Okay, so now let's analyze this thing. So this first term, let's use the Taylor series expansion on the previous page. So we have, we can write this as J at the reference plus the gradient of J at the reference transpose times the deviation, which is going to be epsilon mu plus order norm of epsilon u squared. Does everybody buy that? So I'm just using this equation up here. So this is like my W is W naught plus EU. So this is the deviation from W naught. This is the constant term, the first order, and all the higher order terms. Everybody good with that? Okay. So now imagine that I'm plugging this expression in here. You can see that I'm going to cancel this constant term with this, right? So that will vanish. And so what will remain is the gradient evaluated at vector W naught, that transpose times u, and I will pull the epsilon, which is a scalar, in the front. And then we have this other term, which is going to be, I'll write it like this: order epsilon squared times magnitude of u, right? Because I can pull this out of the squared norm, and I know that that quantity, because of the square, this epsilon turns into an epsilon squared. Okay, and in fact, I can even go one step further. So I can even say this is epsilon squared times order of mu squared. Okay, so basically, I got to write the denominator. So now what we want to do next is we want to look at this quantity as epsilon grows small. That's really the directional derivative as epsilon approaches 0. So what's going to happen is these epsilons will cancel, and so we will have a first term, which is the gradient of j at W naught transpose u. And then when we look at this term, you can see that this has an epsilon squared dependence. We're dividing out one of the epsilons, so now it has an epsilon dependence, but we're taking epsilon to 0. So that means that this thing will vanish when we take this limit. Okay, is everybody good with that? Now let's write this in a slightly more complicated but maybe more intuitive way. We're going to write it as the norm of that gradient transpose u times a fraction, which is going to, in the numerator, be that gradient transpose u, and then in the denominator, it's going to be the norm again actually, sorry, I messed up something here. There should be no transpose in u. So you can get rid of that. This is just the norm of the gradient. Oops. Okay. So hopefully you can see why I can do this. So these two terms cancel, and this equals 1 by assumption. So that's why this equals this. But the reason that I've written it this way is because this second term is the sort of thing that we see in the Cauchy-Schwarz idea, which is that for any vectors A and B, this quantity, which is their inner product divided by their norms, is always some number between 1 and minus 1. So that means this is some number between 1 and minus 1. So if I'm here and I'm moving my looking direction u around, as I look in different directions, if I want to find the steepest direction, the uphill steepest way, I would move u until this is maximized, right? Because this is not a function of u. This is just the gradient magnitude. Sorry. Okay, so Cauchy-Schwarz also tells us that the way to make this thing equal to 1 is when A and B are collinear. They're pointing in the same direction. They might have different lengths, but they're pointing in the same direction. So that says over here, if I want to maximize this, if I want to maximize my directional derivative, I must point u in the direction of the gradient. Okay, so now we know that the steepest direction uphill is the gradient direction. And second of all, if I look in that direction and I look at the slope, at that point, we know this goes to 1 and this is the slope. Okay, so to summarize, the norm of the gradient is the maximum slope, and it occurs when we look in the direction of the gradient. Okay, so this is, gradient tells us the slope is the steepest uphill slope. Okay, so any questions on this? Is it making sense, more or less? Just trying to convince ourselves that really the slope is pointing uphill the gradient is pointing uphill and the norm tells us the slope. Okay, great. So we've done the scalar case of the first order approximation. We've done the vector case, we used that vector forced row approximation to understand the gradient, and now we're going to tackle the matrix case. So the matrix case is really the same as before, except now, since we have a matrix, we're just going to do its sum over the two different dimensions, or different, like the rows and columns of that matrix. So we're going to have J at the reference, big W naught, plus the sum over J, which is going to index over the, I guess it looks like the columns, and I, which indexes over the rows. And we're going to have dj, so this is the derivative with respect to the ijth term at the reference point of matrix W naught, and then we have the deviation Wij minus W naught ij. And then we have a similar double sum for the big O terms. So we're summing all of them at all rows and columns. Okay, so that's just a direct extension of the vector case to one more dimension. Everybody good with that? Okay, so let's now look at rewriting this using matrices. So this is nothing more than the ith row and jth row, ith row, jth column of the gradient. And here we have nothing more than the ith row, jth column of the deviation. To make this look like, actually, to make the 1 over I look like a matrix multiply, we know that we have to make the inner dimension of this product I. So here, the inner dimension is already I. To make the inner dimension of this I, we just transpose that matrix, and now this thing is the jth row and ith column of the transposed gradient matrix. And now when we do this summation over I, what does our matrix algebra tell us? Let's see, is Yang Jiqian Guo here? G-U-O? Okay, what about Eric Jackson? What about Charles Irons? All right, and Jiawei Liang? And Terrell Redding? And Justin Scufa? And Daniel Singer? What about Zhujun Bai? Okay. All right, so maybe, okay, what about Sam Ben Jadirgis? Sorry, I might have mangled that. Sam? No? Okay. Luke Carter? All right, Luke. Finally. All right, so thinking back to linear algebra review, do you see what, if I have like a matrix A and a matrix B, then what, how do I write this? So just for now, this is like A and B. Notice we have a transpose. And we're summing over the inner dimension. You're right, it's A transpose B, but this is a whole matrix, right? So which row and column?
It would be the jth
Exactly, right. So let me remove the red and write the full expression. So this is now using the actual quantities. This is going to be the gradient at the reference transpose times the deviation from the reference, that matrix evaluated at the jth row and the jth column. Good. And now you can see that we are summing the diagonals of this matrix. And if you remember, that is exactly what the trace does. The trace is just the sum of the diagonal elements of a matrix. So really, this sum over J of this is just the trace of that matrix multiplication. We also have this. So we can move this double sum onto the inside, at which point we're taking the sum over all entries of a matrix of the squared quantities. And if you remember, that is what the Frobenius norm does. The squared Frobenius norm is just the sum of the squared entries. So that's how we go from here to here. Okay, and the last step, just like before, this is an equality because it has this term. We get rid of this term and it becomes an approximation. And then what's interesting is that this guy is actually the inner product in the space of real valued matrices. So in linear algebra, when we work with different objects in our space, we have different forms of the inner product. So we saw that when we have vectors, this is the form of the inner product of two real vectors. Does anybody know if one of them was complex, if they were both complex, does anybody know what the inner product would be? So if they were complex valued, you need to conjugate the first one. Okay. The point is that once you go from one space to another, the inner product changes. And so now when we go from vectors to matrices, once again, the inner product changes. So if you have matrices A and B and you take their inner product, you now have the trace of A transpose B. And although that looks kind of, non-intuitive, if you expand this out, it makes a lot more sense. What you do is you do a pointwise multiply of A and B, right? Just multiply all the coefficients, one against the other, and then just sum them all up. So that's the inner product between matrices, and really that's just the exact extension of vectors, right? You do the same thing. You multiply all the elements against each other and then sum them up. Okay. So the cool thing is that we see that this form is essentially always what we have. That you can take the function evaluated at W, you can approximate it as the function evaluated at the reference plus the inner product between the gradient and the deviation. You can do this for scalars, for vectors, for matrices, for tensors. It always works. Okay. And we're getting a little more practice with our linear algebra too. All right, any questions on this? Okay. In this context, the reason we care about linear algebra is because if we program our code using matrix type operations, it runs way faster than if we program it using for loops over the scalar indices, right? So that's the big win. That's why we want to get good at writing things as matrix multiplies and so on. Okay, matrix norms, all that. Okay, so let's do an example where we use this this like second order matrix linear approximation. And so we're going to look at, this is just a toy function that I created. The function of the matrix W is for some fixed vectors A and B, it's going to be A transpose WB, right? So it's going to be row vector, matrix, column vector, and when we're all done, we get a scalar, and we know we need that this is a scalar. Okay, So now the thing is, since we're not experts at vector calculus in this class, we have to transform this to scalar variables, meaning with summations and indices and all that, then do our calculus in the scalar domain, and then come back and build back our matrices. So what we're going to do first is we're going to rewrite this using some summations and scalar quantities from A, W, and B. So let me ask, is Paul Gable here? No. Okay, what about Bird Green? No. What about Frank Hegedus? No. What about Jiaoqi Liu? Okay. So how can I write this with some summations, so without any vectors or matrices? So first of all, how many summations will we need? If I want to write this using summations, do I need 1, 2, 3? How many? 2, exactly. So I'll write the summations, and I'll call one of them J, and I'll call the other one index variable K. So what comes next? We'll just do AJ. Exactly. Right. That is how we write this, this form like that. And so now that we see this, we can see how to get this term. So remember, this is the gradient matrix. This is looking at the J''th row, K''th column of the gradient, which we know is a partial derivative. So in particular, it's dj, and then this is going to be with respect to wj prime k prime, right? That's just some entry in the in that matrix. But the next question is, okay, what actually is this? So let me ask this question. Is Spencer Munch here? Yeah. What do you think? Based on this, I want to take the gradient with respect to wjk, but this j and k they take all values, so I'm looking at this particular combination of j and k. So I'm taking the gradient of this with respect to that particular. So let's think about this in a different way. If I wrote this not with sums, but with it's like a series of terms, I would have a whole bunch of terms. I would look at when j and k are both 0.
Yeah, so you just kind of apply the gradient to that summation equation. So
Yeah.
you're just going to have just the w term.
Well, okay, so for example, let's look at this. So imagine I was taking the gradient with respect to w 0, 0. What would I get?
Or a0 real.
Yeah, exactly. Okay, so we got, so over here, we have A, and what's the index on A?
J.
J prime, right? And B, K prime. Okay, so that's what we have. And so, yeah, and this holds no matter what W is, right? The value of W doesn't even come into this expression. It doesn't depend on W. Okay, so that's what the J''th row and K''th row column of the gradient is. So if I want to write the entire matrix compactly, let's see, is Alex Poteric here? Yeah. So how do I write that very compactly without any indices?
Which
Would it just be the A transpose B?
Close. So if you think about A transpose B, given that A and B are both columns, that would be scalar, right? But this is actually a matrix.
So then it would just be,
So remember that J prime tells us the row index and K prime is the column index. So as we're going down this way, we have J prime. And notice that A is also indexing with J prime. So do you see what it's going to be? Okay, it's just without the transpose, it's the A, right? Because basically we have J prime coming down this way, and then what's the second part of it? Yeah, so what?
which would be B transpose.
Exactly, right. So now we have an outer product which gives us an entire matrix. That's J prime, that's K prime. Okay, so we have an expression, we started with this and we derived the gradient. The gradient matrix is A times B transpose. So now we know how to build our first order linear approximation. We know that we approximate the full JW as JW at the reference plus the trace of the gradient transpose the deviation. The gradient we just derived, so that is AB transpose. That gets transposed again, right? So when I do this AB transpose transpose, since I have a product of things here, when I do the transpose, I have to reverse them and transpose each one. So the A ends up on the right transpose, and the B is like double transposed on the left, so no transpose. Okay, and this is all inside the trace. Is everybody following so far? Okay, now the cool thing about the trace is when you have a product of matrices in the trace, you can swap them, or if you have like CBA, you can rotate them. You can move the back to the front, which is something you usually can't do. But when it's inside the trace, you can. So we can actually swap B with this quantity. So B goes to this side and this. So inside the trace, it's the same. Okay, does everybody understand this step? Okay, and then the final thing is, this is just a scalar, right? Because this is like row matrix column, which is a scalar. And if you take the trace of a scalar, that's nothing more than that scalar. You don't need to take the trace of it. So we can get rid of the trace, and we have this. And now the very last thing is we can do some cancellation of this term and this term, and we are left with this. And, okay, so what's, I don't know, kind of weird or maybe disappointing or surprising is that when we do the linear approximation of this function, we get back the original function, meaning the approximation is perfect. So does this surprise you, or does it kind of make sense? If you saw this and you said, what's the linear approximation of this? Would you think it's that thing itself? In one dimension, if I gave you a line, maybe just an arbitrary line, I said, so this is my function. This is just scalar case, so we can draw it. And I said, what is the linear approximation of J around that point? What would it be? Yes?
Well, I was going to go back to the original because all the core elements of it are linear themselves.
Exactly. Yeah, that's my point, is that when you start with a linear function and you make a linear approximation of it, nothing changes, right? So here, I start with this linear function. I say, what's the linear approximation of that function at this point? It's exactly that same function. nothing changes. So that's what happened in going from here to here. So really the reason I did this is just to get some more practice with linear algebra, to use some of these definitions and tools. Because this is the kind of stuff that shows up everywhere once you start working in this field. Okay, how do we feel about this example? It's kind of making sense? Okay, any questions on it? Okay, great. All right, and now let's take a look at how we do this in NumPy. And there's some actually kind of interesting features of NumPy that we might learn about here. So this is a function we want to program. So there's two different ways you can do this in NumPy. I really shouldn't be saying Python, I should be saying NumPy. Okay, so in NumPy, one way to do matrix multiplication or matrix vector multiplication is using the dot function. So like you can do w dot b to implement this. Now you have another vector, and now you can do a dot that new vector, a dot that new vector. The second way in NumPy to do matrix multiplication is to use the @ symbol. But in this case, you need to transpose this because otherwise it wouldn't be a valid matrix multiply. So there's a couple options here. Now for the gradient, there's also a couple options. We derived this, so now we want to program it. So one way, maybe you could maybe say the most straightforward way is to just do this with the @ function. So in order to do that, you have to turn a from a one-dimensional quantity into a two-dimensional matrix in order to do a matrix multiply with it. So here we're going to reshape a so that the last dimension is 1. Basically, it turns us from a 1D quantity to a 2D quantity. We're going to reshape b, and we're going to transpose b. Now, because we have matrices, we can do the @ sign. Okay. But there's kind of this other really cool trick you can do, and this is what's kind of probably new, is to use this Python broadcasting. So we talked a little bit, or NumPy broadcasting. We talked a little bit about NumPy broadcasting last time, and when we talked about it then, it was kind of like pretty straightforward. Like if you want to multiply two column vectors of the same size, so in MATLAB, I'm trying to think of how I should write this. So usually in a linear algebra textbook, you write the pointwise multiply using this circle with a dot in it. It's called the Hadamard product. But if you want to do this in NumPy, you would simply do a star b, right? And it's smart enough to know, what you actually want to do is an element-wise multiply. So you take these two vectors, you multiply all their elements, and you get a new vector. So now we want to do something else. We want to do this again with broadcasting. So here's this cool thing. Let me illustrate it with this picture. This picture is going to illustrate broadcasting addition, but we can actually do this also with multiplication. So here's the idea. I have a 1D array, A, and another 1D array, B. And what I want to do is I want to essentially turn one of them into a column vector and sort of expand it into a matrix, turn the other one into a row vector, expand that into a matrix, and now add the terms of those two matrices which have the same size. So you can see this is what you get. So you're going to get basically like all combinations of the entries in A and the entries in B in this matrix. So in our code, if you think about it here, we want to do the same thing, but with multiplication. So we have vector A, vector B, and we want to make a matrix. And we know based on the rules of matrix multiplication that, to get like this element, that's going to be this times this. To get the next one, it's going to be this times this, and so on. So it's like this is filled with all combinations of the multiplies in A and B. So it's basically this idea, except there's a multiplication here, and of course these values would change. So is it clear what we're doing? We're trying to do this. And so the cool thing is, with NumPy broadcasting, you can effectively turn A into a matrix using this. You do A, column, comma, or colon, comma, none. And so what this does, it says, okay, make A like 1 dimension bigger and expand the size as needed for the next operation. You don't even have to tell it what the size is. And then for B, you're saying, okay, expand that as a row and make the number of rows in this matrix as big as necessary for this operation. Okay, and at the end of the day, this thing gives you this, but with the multiply. Okay, so this is a cool trick that you can use to do this stuff, and yeah, it's used a lot basically when you code this kind of stuff. Okay, so that's sort of what I wanted to show you is different ways to program this in NumPy. And then all this does is it comes up with some random quantities and plugs them into the function and prints out the result. Okay, any questions about this NumPy broadcasting stuff? We'll see more of it in the future. Okay, so so we just have a couple informational slides here, stuff we actually talked about already. A stationary point of one of these functions, j, is any input that causes the gradient vector to be 0, or the gradient matrix, or whatever it is. And as we know, we use this way back in Unit 2 as a way to find the minimum, because a minimum is one of the places where this happens. But actually, as we talked briefly the other day, there's some other cases where this happens. So here we just have a one-dimensional picture. So we can see the slope is 0 here at a maximum. At exactly that maximum, the slope is 0. At the minimum, the slope is 0. And here we have some pictures of saddle points in 2 dimensions. So if we look in any point there, the gradient is going to be exactly 0 at that point. There's no curvature in any direction. And there's another kind of saddle called a monkey saddle, which is also kind of weird. It's sort of like along this direction, you have something that comes down to a flat point, and then it curves down. And then in the other direction, it's also flat. Okay, so there's different kinds of saddle points, and there's minimizers and maximizers. And so these are the sorts of things, if you say, well, I just want to find the gradient 0, well, okay, are we talking about a minimizer, a maximizer, or a saddle? Okay. Any questions on these? Okay. And then there's this other thing, even if we talk about minimizers or maximizers, we can have global or local ones. So here we have a function that you can see has several minimizers, but often we want to find the lowest point in the function, which is the global minimum. We might not want to find the local minimums. So if all we do is say something like, find me a point where this equals 0, that's a minimum, you still could be looking at local or global minimum. Okay. So that's the kind of situation we find often in machine learning, is that we have complicated functions which have many, many minima, and some of those minima are good and some of them are bad, and we want to find a good one and we want to avoid the bad ones. We'll be talking about how we do this in the future. One of the ways which we can avoid this problem, or one of the ways we do avoid this problem, is anytime we are optimizing or minimizing a convex function, any local minimum is also a global minimum, okay? So that means that, this quadratic is one case where there was only one minimum, and that's great because that's the global minima. Or you can have other cases where maybe the minimum is not unique. In 2 dimensions, maybe we have something like this. So all of these here are minima, but they're all equally good. Okay, so those are both convex functions. So we'll be talking more about convexity later, but convex functions avoid this problem of bad local minima that we might see in machine learning. Okay. And next time we'll talk about gradient descent and how we actually use the gradient for optimization. All right. So we have the midterm exam on Friday. Are there any questions? Any last questions about midterm? Yes.
So I see there's 5 questions in the extra. We will have 5 questions or just 2 like
2. You'll have 2 questions. The questions have multiple parts. The ESSER practice, that was just like a collection of problems. Yeah. Any other questions? Yes.
Letitia said you won't bring us, or we have to print it?
No, it will be in your exam.
Oh, perfect.
Yeah, so you don't have to print it.
Are you expecting us to use the notation you've been using for lectures to represent indices, vectors, and whatnot?
So I like the notation I've been using with the underline because often we have a hat, we have something on top. So sometimes people want to write like an arrow on top. But then if you have like theta hats and the arrow, it gets kind of cumbersome. So that's why I like to put the underline on the bottom. And there are times when it's not clear what you mean. If you write X and you mean like a vector X, but you write X without an underline, you could be saying something different than what you think you're saying. So that's why I highly encourage you guys, when you have a vector or matrix, put an underline under it on the exam so that I can understand exactly what you meant. Okay, great. Any other questions? Okay, see you guys on Friday.